So, Sushant will tell us about algorithms for balanced partition.
Thank you, Avi, and thanks for having me here. I'm going to talk about linear time graph partitioning algorithms, and our main tool will be fast simulation of random walks.
I thought it was almost linear before.
Yes, it's too long for a title. This is joint work with Lorenzo Recchia and Nishit Vishnoi. Okay, why linear time algorithms? We've always talked of efficient algorithms as polynomial time algorithms, but today the graphs that you talk about, for example, the web graph or the social graph, they are close to 1 trillion nodes, and anything much more than linear is really too costly and impractical to be used. So then we set ourselves another lofty goal, which is to try to design linear time algorithms for all fundamental graph problems. You could ask this for maximum matching, for flow problems, or for graph partitioning. So informally, you just want to divide the graph by cutting fewest edges. So as is always, this goal is a little too optimistic. So we'll cut ourselves some slack. We'll say approximate solutions are fine. So well, if you allow me approximate solutions, maximum matching, we know how to do it in near linear time. Flow, we are not so much there. The fastest we know how to do it is an m to the 4/3, and that to a 1 minus epsilon approximation. And in this talk, I'll show you how to get a spectral approximation for balanced separator in linear time. Okay, let's formally define our problem. So I need to define conductance. So we are given a graph G, which is undirected and unweighted. Consider any subset of vertices in this graph. The measure of these sets that we'll use is the volume of the set, which is the sum of the degrees of the vertices inside the set. And given this measure, how do we define the conductance? We are going to take the ratio of the number of the edges crossing the cut upon the volume of the smaller side of the cut. Right? This is defined as conductance, and the conductance of the graph will be defined as the smallest the minimum conductance of any subset of vertices. It's a really fundamental quantity in the study of Markov chains, Riemann manifolds, and of course graph partitioning. So okay, and the most I'm sorry, the colors are a little off, but the most fundamental connection, the first really important connection from algebraic quantities to graph conductance was shown by Cheeger in the context of Riemann manifolds, and then in the discrete setting by Alon and Millman, which connected the conductance of the graph to the second eigenvalue of the Laplacian. So just to remember,
the first eigenvalue of the Laplacian, or the second, the one is first is 0.
The first is 0. So we'll assume G is D regular, although all of this works with irregular graphs. So that's so in that case, we define the Laplacian as identity minus 1 by D, the adjacency matrix of the graph. Okay, so the nice thing about this connection is that it allows you to actually find such a cut that will have value square root of the eigenvalue, and if you use the result of Spielman-Teng, which I'll state later in the talk, it allows you to approximate not just the value of the cut, but actually find the cut in near linear time. And obtaining so differentiating between such a cut, so between values lambda of the conductance and square root lambda, we'll refer to this as the spectral approximation. And this is the kind of approximation we'll achieve.
So Spielman and Teng, though, they have an extra log n factor in there, or?
No, for obtaining this, no.
Oh, okay.
No.
Okay, different Spielman-Teng. Okay.
So this is very simple. You apply power method using Spielman-Teng. So they approximate the second eigenvector using the linear system solver. So there is no log n here. Okay, so now let me define the main problem that we'll work with. That's called the balanced separator problem. So the question we ask is, given a graph, does there exist a balanced cut of conductance at most gamma? So what do I mean by balanced? I mean to say that both the sides have a fractional volume at least b. Okay, this problem has a really rich history, and I'll not be able to do justice to it. So I'll just highlight the most important works in this area. Well, as I mentioned before, it has a wide variety of applications too. This is, for example, in clustering, image segmentation, you can do community detection, and it's a fundamental primitive you'll use in order to do divide and conquer on graphs. Unfortunately, this problem is NP hard, right? I'm guessing all of you've seen this, but now let's say I allow you approximations. What can you do? What guarantees can you give me? So the first algorithm that people came up with after the connection with Cheeger was the recursive eigenvector algorithm. It's a very simple idea. So Cheeger allows you to find a cut. What is the problem with this cut? The problem is that the cut could be really small. I could just hand you 4 vertices which have just one outgoing edge, but that doesn't suffice. It's not a balanced cut. So what do? We first as I said, we use Cheeger to find a cut. We'll remove it from the graph. It's not really that interesting, but we'll remove it and keep it aside.
You remove the small part.
We'll remove the small part, and in the remaining large graph, we'll repeat. We'll repeat until we find a balanced cut, either in one iteration or the union of cuts you found is balanced, right? And again, as I mentioned, what's the problem with this algorithm? It's too slow. Even if you use the fastest implementation for Cheeger, this can really take quadratic time. It can take OMN time in order to find this. Okay. Let me before I move on to faster algorithms, let me first mention the true approximation algorithms for this problem that are known, starting with the work of Leighton-Rao that uses flows, and then a really breakthrough work of Arora and Vazirani using STPs and flow techniques. So Leighton-Rao obtained a log n approximation, ARV obtained a root log n approximation. The issue with with implementing these algorithms is that they really need flows, and as I mentioned before, we don't know how to do flow in near linear time. The fastest we know is n to the 4/3. So well, after a series of work, we've hit that barrier in these works. There's a very interesting work of Madhuri that does not fall into exactly this categorization. It achieves a polylog n approximation given some slightly superlinear time. So you get a trade-off between the approximation and the time. But nevertheless, if you really want like m polylog n, you will not get you can't get a constant here, right? So this is not close to linear. So the class of algorithms I'm going to talk about in this talk that are called spectral algorithms, and again this is also a really large subfield of the work on this problem, and I'm again just highlighting the most important and most relevant works here. So starting with the work of Spielman and Teng that used local random walks in order to give a root gamma polylog. So see, root gamma is the spectral guarantee that we are shooting for, and it's a polylog verse. But instead, what do they give you? They say that their running time is linear in the number of edges and inverse polynomial in 1 over gamma. Inverse polynomial in gamma. So let me remind you. So gamma is the conductance threshold that we are looking for, and gamma can be anything from 1 down to 1 over m. So m over gamma square can actually be way more than linear, right?
What was the difference between the kind of guesses you're getting on the slide and the previous slide?
So Leighton-Rao and ARV, you really get pure approximation algorithms, polylog algorithms, but they are slow, right? Whatever, I mean, even if gamma you're looking for is 1 over log n, you can't break the flow. You have to compute flows, right? So that's an issue. So Madhuri gives you a trade-off, but nevertheless, if you want to go down to linear, you can't get a log n to the constant approximation. Okay, here everything will lose a root gamma, so it's worse than spectral, and often you lose a small polylog also. But the advantage here is if gamma is small, all of these are actually linear, but gamma could also not be small. Sorry, gamma is small. Gamma could be 1 over m. Gamma could be polynomial in n. So Rakesh decomposition is yes, running time is an issue for Rakesh decomposition. That's what Madhuri sort of does. He really brings down Rakesh decomposition to close to linear. In the running time, no. Yes, it's a polylog approximation to gamma. Oh, so it's distinguishing gamma, and see, I can't write an approximation factor because the second set of algorithms is not pure approximation algorithm. So they distinguish gamma and root gamma. This was recursive eigenvector gamma and gamma log n. So the factor is log n. Okay, and sorry, I think I made a mistake. So conductance should be defined as the fraction of edges, right? So I'm sorry. So let me not go back there, but conductance of a cut will be the fraction of edges upon the volume of upon the fractional volume. So then it will be a quantity bounded by 1. Yes.
So root gamma is bigger than gamma.
Yeah. Root gamma is bigger than.
So this doesn't distinguish less than or equal to gamma.
Root gamma is smaller, is bigger.
Is bigger. Yes, smaller than gamma, and yeah, sorry, this is a type. So it's smaller than gamma. You have a really good cut versus a root gamma cut. Okay, just so I think I corrected something that was not a mistake. So let me go back. Conductance. This definition of conductance is actually smaller than 1 because I've defined volume as the sum of edges. So it is smaller than 1, right, Nikhil? Good. So number of edges by the volume of the cut. Good. Okay. So these were pure algorithms, and these are spectral approximation algorithm. So okay, we talked about Spielmann time. Then there were several works here that I am not mentioning, but they are really nice. I'll just highlight the most important ones. And in some sense, the state of the art is this result of Anderson and Perez that uses random walks on sets, and it achieves a root gamma root log n approximation, and in time m over root gamma.
This is regardless of the value of b. You don't regard b as
so okay.
As long as it's a constant, you can believe that it doesn't really.
So in all of these, so b is treated as a constant. So running time dependencies are forgotten, and moreover, actually the guarantees are you'll distinguish that there exists a b balanced cut of conductance less than gamma versus there exists a b by 2 balanced cut of conductance root gamma. So there is a constant loss. Yes, there will, all of these algorithms have a constant loss.
The problem is harder when
if you want exactly b.
no, of course. But
Yes.
for which values of b is the problem?
If you don't mind a constant loss, then smaller gets harder. If you, I mean, yeah. So you usually have 1 over poly 1 over b running time dependencies here. Yes.
Confused. Why do you call m over gamma or gamma squared linear?
This is so it's only linear if gamma is small. Otherwise, it's not linear. But
Why don't we see the next little
yes.
line?
So we achieve the best of both worlds. We actually give a spectral approximation, no polylog loss, and near linear. It's actually m polylog n. There is no polygamma dependence. So it will be fantastic if we could give you just a pure root log n approximation. We don't know how to do that, but we achieve the best from the spectral world. Okay, so here we see that it's sort of the best you can hope from any spectral algorithm. Let's quickly compare it to the other to the previous pure approximation algorithm. So you see running time, as I mentioned, well, all of these algorithms cannot match it because you want either flows or you want graph decompositions, which we don't know how to achieve fast. But if you look at the approximation guarantee, as long as, so if you want these two, as long as gamma is polylog, these are sort of comparable. But if you want, the most interesting comparison is with the work of Madri. So Madri allows you to get very close to linear time. You'll be, I guess we'll all be fine if epsilon is 0.01, right? Almost all applications we don't care. Only theoretically does it make a difference. But then the polylog dependence in C is pretty horrible. Okay, so there is a regime in which a result is actually achieves the best guarantees. Good. So overview of the talk. I'm going to use continuous time random walks to show you this algorithm, and then I'll show you how to simulate random walks fast. So I think the abstract, I said I will focus only on the second part, but I realize it would be it would not be fair if I don't give you a good flavor of what the algorithm is. So I'm going to do both parts.
Just have a question about
Yes.
something that probably doesn't work, but what happens if you just add to the graph to begin with some small set expander of appropriate
So well,
of conductance gamma, more or less.
so
Like in
yeah.
gamma was 1 over log and you'd add the cube.
Right.
And then run your algorithm on it. Wouldn't find some kind of, there wouldn't be small,
So just union.
It could still find a pretty small, in terms of its balancing, because even though it's a better small set expander, it's not still in that regime, right? Even
well, I mean, you have to choose the parameters carefully.
Yeah. So one issue would be construction of these small set expanders with the right
But
parameter.
Yeah, I know. But
Right.
just assume we had them.
Okay.
So is this the issue? Just finding them? Would it work?
No, so the problem is it's with all of these, for example, and even in the hypercube, right? There's a very soft decay in the conductance. So depending on the parameters would have to match up really well in the range, both with the range and the conductance. I can't say that okay everything smaller than 1 over 100 in fractional volume has really high conductance, and after that it just drops to 0 and does not make a difference.
Will never be that
There is a very soft.
conductance higher. I mean, it will depend on the car.
Right. That's all. Yes.
That's why I
Yes.
asked you what
I see, I understand.
Yes. Yes.
Okay, good.
Okay. Great. So let me quickly walk you through a very interesting connection between graph cuts and random walks. So the connection is really intimate. So one direction will be interesting for us. We'll use random walks to find graph cuts, but the connection in the other direction, say from values of graph conductance going to how the mixing time of random walks on graphs it's really interesting and really intimate. I will not get into it. So let me just talk about the works that help you find graph cuts starting from random walks. So the first observation was sort of by Mihail, which said that you can get a Cheeger kind of spectral approximation so you can find a root lambda cut if I actually give you the distribution of a random walk that has mixed well. Right? The Cheeger is usually phrased in terms of the second eigenvalue. I guess, now if you've seen this, it's sort of fairly standard how you'll perform a threshold cut on a.
Wait,
on
that's the statement for me. I mean, what if I give you
morally.
the,
No. So I've not defined what do I mean. Yeah. So take a random walk, let it run for polylog over polygamma time, and then you can find this cut.
Okay.
It's just stating that the power method gets you something close to the second eigenvector.
Okay.
So this is not exactly the statement.
I
Versus
think of Mihail as saying, the original version was you had to solve exactly the eigenvector problem.
yes.
Whereas this, as long as you have a quadratic form, that's
Good. So
diagonal to 1, you'll get something within that.
so you will get that exactly even if you take any distribution and let it run for log n over gamma squared steps,
Okay.
and you will get such something with a good quadratic form,
Right.
and you can round it to.
Okay.
So this distribution will be quite close to the uniform distribution.
It will be close to uniform, but the moment you subtract out the uniform distribution, the remaining will be very close to the second eigenvector, scaled appropriately. Right. So
then it's really given a distribution which is started with sufficient range.
you don't need any randomness. If you let it run for log n over gamma squared, unless you start with the uniform distribution, anything else is perfectly fine. I'm assuming you don't have numerical issues.
Okay.
But
It's just the power method.
yeah, it's just the power method. I didn't want to state it in terms of quadratic forms. It's just
But you have to run it many times to get.
log n by polygamma, yes, in order to get something close to the second. Okay, so this connection has been explored in several works. I'm just talking of works that go from random walks to finding these cuts. So, starting with the Cheeger in Alon, Millman and Mihail, you go from the work of Lovász and Simonovitz, and then Spielman-Teng that I mentioned. They work with usual random walks on graphs. You can define several other natural kinds of random walks on graph. We will use continuous time random walks, but there are other works. For example, Anderson, Chung and Lang use page rank random walks. Anderson and Perez, as I mentioned before, they use random walks on sets. And in this work of Orice and Vishnoi, and in our talk, we will use continuous time random walks. Okay. Good. Let me give you a bird's eye view of a lot of these algorithms. They'll fit vaguely in this framework. You can do a lot of different things, but I just want to give you a flavor of what kind of algorithms to expect for balanced separator. Good. So, the first step in most of these algorithms is you simulate a random walk, either one or several, and as I mentioned, you can try several kinds of random walks: a regular random walk, page rank, evolving sets, and continuous time random walks. The second step is to try to cut the graph. Right, the distribution of these random walks gives you information about the cuts in the graph. Now, using this information, you try to obtain a cut. If you find if there is no low conductance cut, almost always you will get a certificate that if the random walks have been mixed well, then there actually exists no poor conductance cut in the graph. If you find a balanced low conductance cut, we are done. That was our objective. Again, how do you find these cuts? You can do several things. You can do threshold cuts. You can do STP rounding methods. And
you mean if there's no low conductance cut, you get a certificate?
So if there is no low so I mean if there is no low conductance cut, for example, you perform a threshold cut. Okay, if you find no low conductance cut, you get a certificate that actually there is no low conductance cut in the graph, up to some loss.
Okay.
Right. And okay, what if you found an unbalanced cut of conductance in the regime you are looking for, but it's unbalanced? So the third step usually is I want to modify the graph. I want to morally remove these sets that are impeding me from finding the interesting sets. Good. So as we mentioned, the recursive eigenvector algorithm, it removes these sets from the graph, the smaller side. So you'll just cut out the small unbalanced low conductance set. A lot of other algorithms decide, okay, let the cut remain in the graph, but I'll ensure I don't find it again. So what do? I add several edges across the cut, right? And you can decide to do it in different ways. You can use matchings, you can use flows, and we'll actually add stars across this cut. Okay, great. So this almost all the algorithms that I mentioned in the spectral class of algorithms essentially very broadly just fit into this framework, but there is still a lot of things you can try and do with these, and as I mentioned, there are a lot of techniques that have been applied even on top of this framework. Good. So let me define the continuous time random walks that we'll use. So let's say you are given a distribution P0. It's defined as a as a differential equation. It's a diffusion process defined with your Laplacian. So let's not worry about, worry about interpreting the differential equation. Let's see what does it mean for the random walk. If I let the random walk run for time t, means that my transition matrix is exponential of minus TL, where L is the Laplacian of your graph, t is the time you let the random walk run for, and these are called heat-kernel random walks in literature. So this random walk, well, to convince you it's actually a random walk, think of pick a variable as a Poisson variable with mean t, and let that be the length of your random walk. The transition matrix that you get will exactly be this transition matrix for the continuous time random walk. Right. Okay. So this is a theorem. We show that you can reduce the balanced separator question to simulating log squared and heat-kernel random walks and with a specific choice of the time parameter. So gamma is an input. You get if you want to find the best cut, you can do a binary search, but gamma is an input, and we say you differentiate between there exists a cut smaller than gamma versus there exists no cut smaller than root gamma.
So is this theorem false if you use the discrete time random walk, some kind of lazy walk? I mean,
It's true, but the problem is you need to. The only way we know how to simulate these random walks is you have to run for poly 1 over gamma time. Rather, for example,
You're not going to really run the random walk. You have to see it.
yeah, no, I understand, but I'm just wondering whether the theorem is
also.
false if you use discrete time.
So actually, all of the existing results say that try to cut the walk at every step. You take a step, try to cut the walk. You take a step, you try to.
I'm just wondering, do you know
Is it false? I'm not certain. No, but there exists no. But I know that there is no result that says you can do a polylog n. Yeah. So I don't know. I don't know if it's false.
at the end of, I mean, these continuous time random walks are not
Are
false,
yeah, they're very closely related to yeah. So, but I don't know how to do.
It all depends how you average the distribution.
the distances of the length.
No, you look at the distribution after t steps. Now, if you fix t and you do ordinary random walk, that would be rather wide because, for example, Viper time.
Yeah,
So you average.
Right.
Now, the lazy walk averages according to the binomial distribution. Continuous time random walk averages according to the Laplace distribution. You could average according to uniform distribution.
sure.
It's
And
also quite useful, actually.
right, and you're just trying to get, I mean, the difference should be just a factor of polynomial you don't care in the time. So how is that different?
I don't think they are very different once you average.
Yeah.
So the concern is you don't want a poly 1 over gamma. Yeah. So actually, the existing results for at least for continuous time random walks, all of them you had a poly 1 over gamma dependence even in the number of walks. This is what we'll get rid of.
What do you mean by simulating so many random walks, like run different things from different starting points?
Good question. So we'll actually reduce this question to, so there will be log n graphs, log n Laplacians that you will run this random walk for, and for each graph you'll run log n different walks.
But when you say you run a walk, you mean you iteratively compute the distribution?
No, so all I mean is just so plug in this parameter log n by gamma here, and I'll supply p0. Just give me pt for this specific value of t. That's simulating one random walk.
So the full distribution.
So L2 approximation is good, but full distribution, yes. We'll work with an L2.
Factor of n is there anyway because n.
Yes. So great. So at this point, I have no idea how to go to local algorithms using such an approach. So yeah, it's a very interesting question to ask, and I don't know how I've thought about it and I don't know how to do it. Good. Okay, we'll use this result. I'll show you a sketch of this result, and we use techniques from SDPs and exponential updates. They're also known as matrix multiplicative weights. So why have continuous time random walks? They've been used before in several algorithms. What's the nice advantage of using these random walks? So well, in some sense, the exponential is a really nice function. And if you take the exponential of a matrix and you make changes to the matrix, you can track progress using the Golden-Thompson inequality. So starting from the work of Arora and Kale, it was used to design primal dual algorithms essentially. And well, the second thing, as I mentioned, we don't know how to do this with other random walks. It'd be great. Actually, in principle, I believe at least PageRank random walks should give you essentially the same result. But I don't know about regular random walks. Okay, good. So now that we are at the halfway point, let me give you a quick sketch of our algorithm. So our algorithm will fit into the framework we mentioned before, and in that context, it should be fairly easy to see what we're doing. So what we're going to do, the transition matrix we look at is is the continuous time random walk with the parameter log n by gamma. Why log n by gamma? Because it ensures mixing across all cuts of conductance, conductance more than gamma, right. So, your focus is on cuts of conductance less than gamma. So, if I started with a random walk with a vertex I will obtain a probability distribution and a probability distribution in Rn, which will be WEI. Now, I can think of this as a vector assignment to EI, as a vector assignment to the vertex I, and that lets me get an embedding in n dimensions, right. I have a vector for every vertex. So, long vectors in this random walk. So what is each vector? Each vector is just a transition matrix with, it's a random walk starting from one vertex. So what a long vector means that it's a walk that has not mixed well, right. If it's a great, so intuitively we want to think of, for example, this bunch of long vectors here as a small cut of low conductance in the graph, right. Great, and our measure for progress is how close each of these random walks is to stationarity. So you look at each random walk and you look at how far you are from the stationary distribution. This is the L2 squared norm, and our measure of progress will be this potential with respect to the set of vertices. So you sum up over all random walks starting from each single vertex. So you don't need to remember the exact formula, just vaguely it's a measure of progress of how close you are to stationarity, right. So what's the first thing we'll try? Well, the easiest case is where all of these random walks are small, all of these vectors are small. Then you basically get a certificate that all random walks have mixed. So there are no small cuts in the graph, right. So this is great. Okay, let's say, well, so I just wanted to say that you measure this softly. You sort of measure the distance from stationarity. If it's polynomially small, you're done. If it's not small, we are going to try and round it.
I mean, so that part, this potential function is also very geared towards looking for a balanced cut only instead of a very small one, right? Because, you know, if there was sort of a violating one, I mean, if it were small, it wouldn't potentially contribute.
Right. You really, let me, I mean, one helpful way, if you've seen this, might be to probably think connected to the balanced separator SDP. Okay. It's sort of the same thing, right? Since you are looking for balanced cuts, you can just normalize to say that the sum of the vectors are spread out, and then you don't care. Good. So we are in the case. So we are assuming the walks have not mixed. Okay. Now what are we going to try to do? We are going to try to find a cut. Okay. So let's try to do the standard Cheeger rounding. So we'll project along a random direction, and you pick a threshold cut. We'll try to find the most balanced cut. So again, if you find a balanced cut of small conductance, you're done. This is all we are looking for. If we don't find something, now we need to figure out how to modify the graph, right? Because there are small cuts in the graph that are impeding us from finding the interesting cuts. Good. So we didn't find a balanced cut. So in this case, we show that there actually exists a ball cut. What do I mean by a ball cut? You sort of cut off all the small vectors, and the cut consists of the long vectors. So all of these long vectors together, and what do these vectors together satisfy? One, they satisfy that it's a good conductance cut. Second, they actually satisfy that it accounts for most of the potential on like most of the reason why your random walks have not mixed.
You have to be careful in choosing this poly n. I mean, which poly it is?
No, it doesn't make much of a difference, but essentially 1 over n suffices. Yeah, this doesn't make. It'll only make a difference in how many constant in front of the log. Good. So what should you think of this cut as? Think of it as that we are finding all the unbalanced cuts of low conductance in the graph. We are finding them together. This is morally what the idea is. This is the reason that recursive eigenvector was slow. You would find a small cut of constant number of vertices every time, right? And then you would get quadratic time. So here morally we essentially find all the unbalanced cuts of low conductance together, and then and then we want to remove these cuts. So how do we decide to remove these cuts? We'll add edges from all the vertices, all the long vectors, all the vertices in the cut to all the remaining vertices. So it wouldn't be so nice to show it in this diagram, but what we actually do is from every vertex in the cut that we find, we add a star to all the vertices, right? So that will, in particular across this cut, it will give you a lot of edges. Yes, according to the degrees.
And you are doing it logarithmically many times, so it has to account for this also, because overall, if you keep repeating this, you will add a lot of weight to the edges.
But it's only, the cut is really small, right? The cut is unbalanced. If it was balanced, I would already be done.
That's the only case you'd be adding like quadratic.
Yeah, so I should have mentioned this, that S is, so we can assume that S is unbalanced. If S was balanced, you're already done, right? And so this is also the other thing you'll do. We'll keep collecting these sets, and if at any time all the union of these sets become balanced, you're done. Good.
Probably don't literally add a star, you just a sample.
No, we do add a star. So actually, that's sort of crucial. Let me mention that point once I finish this. Good. So as I mentioned, this will help us sort of soft remove these unbalanced cuts. And what it helps us is that it improves the convergence to stationarity by in terms of our potential by a constant factor, right? And we'll start from basically we'll start from n at most, and we need to only go down to 1 over poly n. So basically log n rounds would suffice for us.
Wait, explain that again.
So W prime is your new random walk after adding these edges. All I'm saying is that there's a constant factor improvement in your convergence.
Is that clear?
It's not obvious.
Or this inequality?
It's not obvious, but it requires say Golden-Thomson for the analysis.
And you are not telling us yet also how to calculate these things, because there seems to be n vectors.
Yes, very good. So we, for efficiency, we'll actually just project all these vectors in log n dimensions. Okay, so we'll use the Johnson-Lindner-Strauss lemma. We'll project them in log n dimensions. So okay, so technically now it's no longer a random walk, because I'll apply the matrix W to a random Gaussian vector. But morally, it is still a random walk. I'm trying to obtain some combination of these random walks, right? And coming back to that point. Okay, so I was hoping somebody would point it out, but I'm actually adding a quadratic number of edges into the graph, right?
That's what I was hoping you were sampling.
Yes, so it's actually a very crucial point when we come to simulate these random walks, because I can't afford to give just a quadratic, essentially a really dense graph. But so what's the advantage that we use here in order to still simulate these random walks fast?
I mean, it's very structured. Right?
Yes, exactly. So the random so the matrix that you're adding to your, let's say, the adjacency matrix, it's a low rank. It's a complete bipartite graph, but it'll be a low rank graph. So it will matrix operation will still be cheap.
Right.
Yeah.
Yep.
Yes. So yes, we'll repeat. Actually, not rank 1, because it will be rank the size of the set. Sorry? Because of the, no, because I add a star from each of them. Oh yes. Yes. So there are no, so but the weights will be same. So yeah, good. So it's rank 1 in every iteration.
Why is it quadratic number of edges? It's just linear in times linear in S.
So S could be n over 100, and I could be looking for n over third set, right? So it could definitely be quadratic. We don't know that. Great. Okay, I want to close the algorithm part here. Right? It's morally we've reduced the question of finding these balanced cuts in the graph to simulating random continuous time random walks. And so we are given a Laplacian, a time step, and a vector v. I want you to compute e to the minus tau l v. This is what we reduced to the question to. Now, you can compute this exactly, but it's really costly. It requires n cube time in order to, so you'll diagonalize and then exponentiate each eigenvalue, but it's too costly. So what are we going to do? We are instead going to approximate this, and we are going to approximate it really fast, and that's what the rest of the talk is going to be about. Good, simulating random walks. So just restating the objective. So you're given a time step tau, the Laplacian L, you're given a vector v and an error parameter delta. You want to approximate e to the minus tau L v, right? So e to the minus tau L is your n is an n by n matrix. E to the minus tau L v then is a vector, and you want to approximate it up to a delta L2 error, and this L2 error suffices for our algorithm.
So L is given. You want linear time in M or in
yes, we want linear time in M actually, number of edges in the original graph. So other than saying that the remaining added edges are of low structure, I sort of skirt that issue currently, because yeah, it doesn't. There are a couple small ideas there, but nothing substantial. So, like I think this is this gives you a flavor of exactly what we really want to do. Good. What's the first thing that we want to try, and it's actually been tried in several algorithms, is that you want to use a Taylor's approximation. So you just Taylor approximate e to the minus tau L and truncate after, let's say, k terms. It works pretty well, except for the fact that you need too many terms. You require terms that are linear in your parameter tau and logarithmic in the error you are looking for. Now, logarithmic in the error is fine for us. Our error would look like inverse polynomial in n, so that's just a log n factor. The problem is the tau term, because tau will be essentially 1 over gamma for us, and that's too much. We can't afford to lose this much time. Great. So this is too slow for us.
So you're going to do this for any L that looks like the Laplacian of a graph.
So okay. So well, to be precise, we basically do it for any SDD matrix, any symmetric and diagonally dominant. So you can add sort of constant terms anywhere on the diagonal, let's say, and that's fine.
And also with adding on constant rank.
You have to. So yeah. So the theorem, we sort of tailor it to the kind of matrices we want. I can't give you a general theorem saying that you give me a low rank addition and it's fine. So yeah. So morally, currently you should just assume I'm given a SDD matrix, even in particular Laplacian, and that will show you all the ideas with that. Good. So Taylor's approximation doesn't work. So maybe what's the next idea we want to try? We want to do it faster, and it's an idea that's been used in several results. Can you ask for better polynomial approximations?
So we should think about the old one as the power method, and this is like Chebyshev types of things.
Yes.
Okay.
Yes. If you've seen those, this is exactly that connection. And yes, there are better polynomials. So okay, I just make an observation that so the Laplacian has eigenvalues between 0 and 2. So it suffices if I approximate the exponential function on the interval 0 to tau. Good. So here's the theorem. There actually exist polynomials that go with degree root tau instead of tau as we had for the power series. These go for root tau, and there's a polylog dependence in 1 over delta, which is the error, and it lets you approximate the exponential. It does. Great. So good. Let me just say that so we proved this theorem, but we didn't find a reference in approximation theory literature. Nevertheless, this theorem is known. We figured out later. There are actually several people have discovered it in sort of independently. So I will not stake any claims on this result, but this allows us to plug it in with our algorithm. So as a warm up, it will allow us to find a cut of root gamma in m over root gamma time, right? And this is already better than the other spectral algorithms. It's for example, the comparison is Anderson and Perez. It gives you the same running time as Anderson and Perez, but it gives you a better guarantee. Good, but this is still not sufficient. We really want near linear.
So you have it wrong. Near linear is the run.
Oh, right. It should point here. Sorry. Good. Can we ask for even better polynomials with no dependence on tau? Sounds really unlikely, and we actually show that it's not true. You can't hope for much better than this.
What about rational functions? Or
good, that'll be the next slide.
Okay.
So, but I'll say in some caveats there too. But so any polynomial which achieves the approximation we want over an interval 0 tau or 0 2 tau must have root tau dependence on the degree. Okay, we prove this theorem by using Markov's theorem in approximation theory. If some of you have seen it, it's the same reason why Grover search is optimal for quantum algorithms. It's a simple but powerful theorem, and we show that this essentially says you can't use polynomials to do better. So good, as Ankur has already pointed out, how can we go beyond polynomials? We can go beyond polynomials by using rational functions, and this is exactly what we do.
Sparse won't help though; it's still a polynomial. I mean, Chebyshev is
not clear. How do you compute a degree higher than root tau? Let's say, right? Because I can't do repeated squaring. I don't have that much. I can't afford a dense to store and compute a dense matrix. So sparse doesn't really help us. So great. So rational functions. Here's a beautiful result of Safshon-Eisenberger. It says that you can approximate the exponential function by a polynomial in 1 by 1 plus x by k. Right. So I mean we all know that if I let 1 by 1 plus x by k to the k goes to 1 e to the minus x, but that doesn't, it turns out to have very poor convergence. But if you allow me a degree k polynomial in this rational function 1 by 1 plus x by k, I can get geometric convergence 2 to the minus k. That's the error. And I think it's really fantastic that you can get such great convergence. Moreover, you get this over the whole interval 0 infinity.
So I've seen this in the I've seen approximating different functions like things like the absolute value of x by rational functions, where I think it was used by like PP is closed under intersection, like right now. Is there any connection between? Is one intuitive from the other, or is there any connection at all, or not really?
Yeah, I don't think so.
Okay, I'm just curious, what sorts of functions can you hope for this type of geometric?
Can you hope for a geometric convergence? I really don't know. It's sort of mysterious to me that you can even, I would not guess that you can get geometric decay. It's really fun, and over the whole interval. I'm not even saying you restrict the interval, so I really have no clue as to what to expect. But the proof is very readable, and I can tell you vaguely about it after the talk. Good, as I mentioned, geometric decay. So this gives us a logarithmic dependence on the error that we want. Great. So
anyway, e to the minus x is basically 0. So you look at 1 over x to the k, that's almost getting geometric convergence everywhere except in the interval 0 to 2.
No. So actually, for example, if you take the naive approximation, which is 1 plus x by k to the k, right, which is you use it very on a very everyday basis. That approximation actually has an 1 over k convergence. Really poor. It's so that's why it's pretty surprising such a geometric decay. Get it near 0. That's right. Yeah. But nevertheless, the exponential function decays so fast that your polynomial might still, you might have to worry about it even beyond a small range. Good. So what will this allow us to do, which I'll show you in the next 10 minutes, is to approximate the continuous time random walks, and I'll reduce it to solving linear systems. Approximating the inverse. So C is some scalar, constant times identity plus a Laplacian inverse. Great, and this inverse now we can use the result of Spielman and Teng to approximate these inverse. So what's the result of Spielman and Teng that we use? I'll state it informally. It basically says that we can compute these inverses essentially in near linear time. Good. So let's say I assume we are given this polynomial explicitly, and the Spielman-Teng computation was exact. We'll be done.
So that's interesting, right? So now there's no need of exponential. That's what you've shown. You never need to do exponential.
Yes, but so only morally. I can't tell you that just compute one inverse and do an update. You'll have to compute several inverses, combine them together to essentially get an approximation to an exponential, and then do an update.
I see. So
Yeah, so it's no real better than thinking in terms of approximating the exponential. Good, but it has two major problems. One, that this result is existential. Two is that the Spielman it's existent. It gives you an algorithm, but it's a not so nice algorithm. We don't know the constants that you get are really not so easy to compute. But so the point is we'll be able to get around this, and we don't have to worry about can you compute those coefficients, with what accuracy can you compute them, how fast can you compute them.
Because you'll be able to do as well as the best, K
as the best degree K polynomial. And we have to handle the fact that the approximation using Spielman-Teng it's only approximate inverse computation, right? Good. As always, I'm running behind time. So here's the result we show. We show that you can approximate the continuous time random walk in time that's linear in the number of edges in the Laplacian, logarithmic in the error polylogarithmic in the error that you want. So there's a log tau factor. I've stated it here because that's how we state it in the paper, but you actually don't need the log tau factor. So you can do it independent of the time that you want to simulate it for. Great. So I will try to do this a little quickly. The first part I'll focus on is that we don't know the polynomial that we are trying to compute. So we'll use this it's really nice method from numerical linear algebra called Lanczos method. So let me remind you. So we fixed this matrix B. So this was the function that we were looking for, right? So identity plus tau L by K inverse, and we want to approximate f of B, where f is such that f of B is e to the minus tau L, right? This is our objective, and our goal is to approximate f of B as well as any degree K polynomial. Good, and Lanczos method will allow us to do that. So it has some really nice properties. One, first thing, it allows you to go from real approximation to matrices, which is obvious if you know the polynomial. But the advantage here is that an existence result is good enough. If you know there exists a good approximating polynomial, you can go to matrices. And the third advantage is that if your approximation degree is small, then the process is really efficient.
So you were really lucky that SSV gave it as a polynomial and it was one particular.
Great. Yes. If it was, it's not an arbitrary rational function. If it was an arbitrary rational function, it would be, bets would be off. So good. So let's quickly see this. So let's say P is any degree K polynomial. Well, the first obvious observation is that the vector you are looking for, P of B V, is in the span of the vectors. Sorry?
P is the F you wanted.
No, P is a degree K polynomial.
Oh,
That you
for
want to
P
be an
itself.
approximation.
Yes.
Yeah,
Yeah.
that's right. Okay.
So it's in the span of these vectors V B V to B to the K V. This is called the Krylov subspace of order K. So let's say you have an orthonormal basis for this subspace V0 to Vk. So think of stacking them together. So V is the basis change matrix. So morally, so B is an n by n matrix. It's an operator in the n dimensions. So you can restrict it to this subspace. I can restrict it to T, which is so formally this is it, but morally I can restrict it to a K by K matrix, which defines the operator within this subspace, right? And now within this subspace, we know that you have V, BV till B to the KV. Should sort of really suggest you that I can compute all degree K terms in B multiplied by V just using T, right? I don't really care about the parts that are outside the subspace. And so this is essentially what you can show. You can show that for any degree k polynomial, you can compute PBV. So P is a degree k polynomial, and this is an n-dimensional vector by essentially by using the operator T, which is B restricted to this subspace. Good. So what would you gain? You would gain that T is a really small matrix. It's k by k. K is logarithmic for us. It's much smaller than. So you can do any computation. In particular, I can diagonalize it and exponentiate it explicitly. Good. So all of this is just a caveat again that this is not. This is all very well known. I'm just redoing it here for the people for people who are not aware of this, and I think it's beautiful. It's if nothing, you should take back this from the talk. So let me convince you quickly why this is true. What's a projection onto this subspace? The projection will be V transpose, where V is our basis change matrix. So this is an n by n matrix, and it projects any vector down to this subspace. So okay, so let me do this for a very simple case, say B squared V. So the first thing you observe is that we know that V is in the subspace, BV is in the subspace, and B squared V, all three vectors are in the subspace. So I can essentially apply a projection at every step. So I get pi B, and pi V, right? Now I can just rewrite pi as VV transpose and rearrange to get it in terms of T, which is your k by k operator, right? Good. So now what are you going to guess for your function? We are going to guess that you can approximate this function also using T, and that'll be your approximation. Again, saying that T is a much smaller matrix. So even if f is a complicated function, you can diagonalize it, and as long as you can compute that function on the reals, you can compute it for the matrix. Good. I want to show you why it's like the best polynomial. So this is the error we want to. So f of BV is what we want to compute, and this is our approximation that we are returning. So let's say Px is a good, say even think of the best degree k polynomial approximating the function. So what I'll do is I'll write the f of x as the polynomial P and a remainder function, right? So just writing T to be sure. So now I'll substitute f as P plus the error in both the terms. Now the nice thing is that the polynomial parts are equal. This is what we showed, right? All the polynomial parts are computed exactly, okay, and then that means our error is determined only by the error function applied to the matrix B and applied to the matrix T. So let me skip over this. This is nothing. So basically, I've essentially shown you that I can pick the best. So another point, I use P only in the analysis. So it says that if I output this approximation using the small matrix T, the quality of the error is determined by the best degree k polynomial approximation.
Can you go back to the previous slide and show us again what the algorithm was?
The algorithm?
What the algorithm was?
For computing the exponential? Yeah. It's okay. So let me tell you. So you compute this subspace, V, the Krylov subspace, V, BV, B squared V, B to the KV. In this subspace, take an orthogonal basis. Using this basis, project your operator B down to this subspace. Okay. So it's not just a projection. You lose some parts, the parts that it acts on outside the subspace, but now it's a k by k matrix operating within this subspace, right? And we sort of give a guarantee that if you are computing a small degree polynomial in B multiplied by V, you can compute it just using this small matrix, right? And now that you can compute degree k polynomials exactly, your guess is that a good approximation is that I'll use this matrix to compute the function itself, what I'm looking for, right? And this is your approximation exactly, where V is the basis change matrix and T is your k by k operator, right? So this is the approximation algorithm for the exponential.
So for this to work, you need R to be small pointwise on the
On the spectrum. Great. So the error. So both these terms are bounded by R on the spectrum of B and T, and spectrum of T is essentially controlled by the spectrum of B. It's bounded by the spectrum of B. So as long as I can bound the remainder, a polynomial approximation on lambda min to lambda max of B, I'm done. Right? That's all you want. So you get an error guarantee that's determined by the best polynomial. This is fantastic, right? So all we need to do is we'll use Lanczos with a logarithmic k, and f and b as desired, and we'll be done. Of course, there's a before I go there. So what's a cost? It's really efficient. I mean, I'm doing nothing. I do k multiplications by b. K is logarithmic. I construct this basis. So again, since it's only log n vectors, it takes n log squared n time to construct this basis, and I need to diagonalize t when I'm computing the approximation. All of this just takes near linear time. So this is really good. This is what we want to do for. But of course, we've not answered the question that we just cannot compute this. We have no idea how to compute this basis or the subspace. We don't know how to do these multiplications exactly, right? So let me point out in more detail why the method itself is insufficient. So recall we needed this basis, right, for the Kreyler subspace. So we said the Spielmann-Teng result is approximate, so you get errors. So every time you multiply by a b here, you get an error, right? So the subspace that you get and the operator and the basis, everything is approximate, right? We have, so you know sort of term by term error, you can bound that, but all of these computations are iterative. So error in the first step cascades down to computations in several steps. So it's totally not obvious that the error is bounded. Rather, if the function you're computing is not nice, all bets are off. Okay, and another issue actually is that t is not the t, which was the operator restricted to the subspace that you will compute. It's not even symmetric, and we really use this crucially. The nice spectral properties that you get by symmetry, we use that crucially. So you lose that. So this one we've sort of fixed easily. We say, okay, symmetrize the matrix and work with it. Like, okay, sort of the natural thing you would try, but still leaves us with the question of, okay, bound the error when you symmetrize. Okay, so I'm essentially done with my time limit. So I'm going to give you just few seconds on what would you try. So basically, you again split f into two parts. You split it into the polynomial part and the error part, right? So f is approximated as a polynomial and an error function. So this was 0, but now this will take most of our work in order to bound. So the error part we can sort of again bound because these polynomials are really nice. So we get from the result, from the approximation result, we'll quickly get that these parts are small. For this part, you need a lot of work and it's very messy, several pages of calculations, but you can basically bound it term by term, and you bound the sum of the coefficients here, so you can bound it. Let me not say any more about it other than the fact that it's messy, it's very important for our work, but nevertheless the advantage we have is that Spielmann-Teng has a logarithmic dependence on the error, right? So any polynomially large error is fine for us. We can lose, so you can have a lot of slack while doing this analysis.
So bounding the sum of coefficients of pk means you need to get some explicit.
Some is, but the nice thing is k is logarithmic, so even exponential in k is fine for us.
So in fact, you can compute this polynomial. You have time to compute this polynomial.
So
I mean, the whole point that it's not explicit in the Shanghai this result, BSS, whatever it is. When k is small, you can just try to, I mean, some solution to some convex program, right?
yes.
Just get
Actually, no. I mean, the best infinity approximation is not really. Well, okay, on the spectrum.
on the spectrum.
But you don't know the spectrum of B. You can compute the spectrum of T, but you don't know the spectrum of B.
Wait, but I mean, you just need it for the exponential. I mean, yeah.
Oh, but then it's not a convex program, right? The moment you write it as an optimization over an interval, it's not a convex program.
You can take a discrete net, right? Because you're only looking at small k.
Yeah, you can try to do that. but I mean, if you can get the best thing, why I don't see why not. I mean, I think this is sort of unnecessary. There might and there should be probably a more cleaner analysis, which you can actually do. There is a way to do it if you sort of assume that Spielmann-Teng was a linear operator, in the sense right, then you are multiplying by a different linear operator. You can do a better analysis, but the problem is we build on Spielmann-Teng, so we don't get exactly a linear operator. If it's a linear operator, you can do a nicer analysis than doing such a hairy analysis by bounding all the coefficients and everything.
And the SDD condition also considers the
We actually need it because we are adding these. So the stars that we add, they essentially become the Laplacian of those stars looks like the projection of a diagonal matrix. Okay, so those diagonal matrices get added to your Laplacian. So you need need to actually invert SDD matrices, not just Laplacian. And the projection we sort of handle by rank 1 changes to. So yeah, so we really need not just Spielmann-Teng. If you give me Spielmann-Teng, I can exponentiate SDD matrices. That's totally fine. But we need to do a little more work. But yeah, so that's but morally, the moment you can do fast inverse computation, you can do fast exponentiation. That's a moral here. Good. So let me just remind you what we just did. So once you plug in this error analysis, which I didn't show you really, but with the Lanczos method, you get fast random walks, nearly linear time continuous time random walks. And fast random walks we plug in with an algorithm, and you get an fast algorithm for balanced separator. Great. Let me conclude. I'm sorry, I'm over time. So we reduce balanced separator to simulating polylog random walks. Next, we showed how to approximate these random walks in near linear time, and both these by themselves can be used as primitives in trying to design better near linear time algorithms. And of course, that shouldn't be there already. I'd like to see more applications. I think it's nice, and maybe we can do more applications. Maybe graph decomposition. So not just two parts, several parts, where every part is essentially an expander. Can we do that in near linear time? That would be great. Can we do small set expansion in near linear time? And I think the big main question here is, can you get the best approximation, which is a root log n approximation in near linear time? Okay, that would be all. Thanks.